Hey everyone, what's going on? So in this video, we're going to be talking about Chapter 13, which is Oscillations about Equilibrium. So I'm not going to lie to you, this is my favorite topic, and I'll talk about it in a bit why. But we're going to be going over some pertinent equations, and we're going to dip into each of the topics covered in Chapter 13, and I have 3 sample problems ready. So just as a forewarning, for anybody who did take extensive notes in my last few discussions, especially for the one this past week, this is going to be very, very similar as far as the pertinent equations aspect. So feel free to skip to problem 1, 2, and 3. So let's get into it. So considering that this chapter is really on oscillations at all, we need to consider the specific case of periodic motion, which is where we'll really be introduced to this sort of oscillatory motion. So you can't describe periodic motion without describing your period. So our period, we're going to say, is the change in our time from peak to peak, trough to trough, or really any 2 points that are going to be identical. And what I mean by that is if we draw out some sine wave, and I'm purposely going to add this little bit on the bottom, draw out this sine wave, then we can say that from trough to trough, so this distance right here, or peak to peak, or any 2 identical points where let's say it's going from positive to negative and from positive to negative at this point right here, this would also be considered 2 of those identical points. And it's that change in time that will define our period. So you can't really talk about period without talking about frequency. So how you get from period to frequency is that the frequency is just the reciprocal of period. So if you have your period, you have your frequency, and vice versa. So another few things I want to really talk about with this graph right here is that what are the axes going to actually define in this aspect? And what are some key points of our wave? Because waves are going to dominate this chapter. So if we have on this side up here, whatever our displacement is, let's call it x. And then this is our time series, let's say t. Then there are 2 other things we can really describe in this just by looking at it. So we can say that this little bit, if this is a sine graph, then we know that the sine of 0 is equal to 0. But if we have some little shift right here, then we'll call this phi, where it'll be called our phase shift. So phi is going to be equal to our phase shift. It's just any displacement away from our 0 point for any trigonometric function we're dealing with. Our maximum height, too, we're going to call A, and that'll be our amplitude. And then, of course, peak to peak, trough to trough, that's our period. So if we wanted to describe any point along this wave, then how can we really do it? So we'll say that our position in simple harmonic motion, which is a very specific type of motion, will have this following equation, where it's our amplitude times the cosine of 2 pi divided by our period times time plus phi will be our position. Now, what we can also describe this as is our amplitude times the cosine of, well, this right here, 2 pi over t. This is going to be our angular frequency, omega. So we'll say that omega down here, just to keep it with everything else that we'll define in a bit, will be equal to 2 pi divided by our period, or based on this equation that we had right here, 2 pi times our frequency. So we'll say that this is going to be omega t plus phi, some phase shift. Now, something to keep in mind too is this omega t, well, this is equal to theta. So we get that we can describe this as our amplitude times our cosine of theta plus phi. This one right here will be the one that I find is used more frequently than most. So if you had to write any of them down, I definitely would say do this one. So we have our position, but what about things like our velocity and our acceleration? We know that they're related to each other in a bunch of different ways, but without falling into derivative land, where we know that the derivative of position is velocity and the derivative of velocity is acceleration, then I'm just going to give you those values. So by taking the first derivative of the above equation that I just circled, this one right here, then we get that our velocity is going to be equal to our negative amplitude times omega times the sine of omega t plus phi. And our acceleration is going to be equal to our negative amplitude times omega squared times the cosine of omega t plus phi. Now, a really subtle note is that our amplitude is going to equal the maximum position if there's nothing else acting on it. What I mean by that is if we don't have any bit of the cosine term, then it's just going to be our maximum position. Now, if we want to do the same thing with our velocity or our acceleration, then we'd find that our Vmax and our Amax, where they are going to equal our amplitude times omega and then amplitude times omega squared. Okay. So now that we kind of have this stuff defined, let's start putting it in terms of really real apparatus that we've worked with before, such as a pendulum or a spring mass system. So if we want to consider a vertical spring mass system, or rather not even vertical, if we want to consider just a horizontal mass system, let's say, then the period, well, that's going to equal 2 pi over omega. And something that we can find in simple harmonic motion is that our omega is going to be equal to the square root of k over m. I'm going to save the derivation for this, but you guys can find the full derivation for this in your lab manual for lab 9. So by making the substitution, we get that our period is going to be equal to 2 pi times the square root of our mass divided by our spring constant. This equation is very important, and I would highly, highly recommend having this one in your toolbox. Same thing with this relationship right here. So the next one I really want to discuss is the pendulum, where it kind of takes exactly the same idea as what we did for the spring, but now defines it in terms of our gravity and the length of our pendulum. So specifically for the case of when we have a pendulum, let's say at some pivot point right here, and all of the mass is constrained to the end of the pendulum with some length L as the string, then we can say that the period is going to be equal to 2 pi over omega, which will be equal to 2 pi times the square root of L over G, where this is going to be the length of our pendulum, and this is the gravity, the acceleration due to gravity of whatever object we are on. So just looking at this relationship, we can see that if we are on a different planet, let's say going back to the video for chapter 12, if we were sitting on an asteroid where its acceleration due to gravity is something like I don't know, like 6 times 10 to the negative fourth meters per second squared, our period is going to be very large because we're dividing by a very, very small number. So this is a very specific case of us using a pendulum where it's just for a point mass. Or putting it in terms of something else, it's not just a point mass, it'll be all of the mass is constrained to the end. Of the length, L. But this isn't the only kind of pendulum that we have. We have this thing called a physical pendulum. Call this physical pendulum. And what the physical pendulum is a pendulum that rotates about some axis of rotation. And it has a non-negligible mass throughout the entirety of the object. So if we had something like a rod here, then we would have it defined by some length L. It also has some mass M. However, when we write out, I'm going to write out the equation here that'll show that this isn't all that we need. So our period is going to be equal to 2 pi times the square root of lowercase l, which I'll define in a second, divided by g, times the square root of the moment of inertia of our rod, or rather our object that is going to be acting as the pendulum, divided by the mass times this lowercase l squared again. So this lowercase l, that's going to be equal to the distance from our pivot. Now, something to note here too is if we're dealing with something like our mass times gravity, this distance from the pivot is going to be to the center of mass of whatever object we are considering. So if the center of mass just so happens to be right in the center, if this is a uniform rod, then this as our center of mass would kind of tell us that this length here is going to be our lowercase l, and hence L over 2. So I'll do a problem on this a little bit later where it'll kind of show this in action. But this equation right here will be how you find your period for a physical pendulum. So kind of getting out of the simple harmonic motion aspect of this, there's also pretty much every real type of oscillation has some sort of friction in some way or another. And that sort of friction comes out in the way of damping. So damping, I'll just write damping as this. We're going to define that by a variable b. And this is really just some constant that describes the decay of our wave, or rather, it's kind of the forces that are going to be acting against the amplitude every single time that we are making a pass or as our time evolves. So for our underdamped case, and I specifically say underdamped, and we'll get into the other two in just a moment, the way this would kind of look is like this, where if this is t right here, and this is our position x, then this whole width here, and this one as well, will be a naught, and we'll say this, a negative a naught, our initial amplitudes. But the path, if you kind of drew along the peaks, this curve is going to equal E, which is a natural number. If you guys aren't familiar with E, please let me know. But this is like log base E, so natural log, which is also equal to log base E, it's this number right here. It comes out to, if I'm not mistaken, something like either 2.7 or 2.1, something along those lines. But it's another very important relationship, somewhat similar to that of pi. So this E is going to be equal to negative BT divided by 2M. So we just defined B. T is the time in which we evolve, and it's divided by 2 times the mass. So our mass becomes important when we're talking about damping. So if we wanted to write this as a function of our amplitude, let's say our amplitude as time evolves is going to equal our initial amplitude times e to the negative bt divided by 2m. So putting this into the equation for our position, where we know that our position is going to be equal to our amplitude times our cosine of omega t plus phi. Well, let's write in our a as a of t. And we get that our position at any time, including the damping, would be a naught times e to the negative bt divided by 2m times the cosine of omega t plus phi. I've used this equation so much. So I would highly recommend that if you guys want to use this for another time, it'll definitely be redefined to you if you need to use it at a later course. But this is a very, very important equation in terms of physics. So remember, this is for damping. Now, I said something before that this is going to be our underdamped case. So instead of defining exactly what our underdamped case is, let's describe overdamped. Now, overdamped is going to be an oscillation where we're not actually really oscillating at all. We have some initial amplitude, but the way this graph would kind of look is if we have some initial amplitude, a naught, then it's just going to slowly come to equilibrium. It's not going to pass to the other side at all. And the higher our damping coefficient is, the longer it takes to be able to actually do that. So the overdamped case is that it moves very slowly to equilibrium. So kind of looking back at the underdamped case, this is when it'll oscillate back and forth because it has a damping coefficient that's low enough that allows it to be able to do that. The critically damped system is right in the middle. And what it states is it's kind of similar to the overdamped case, but there exists a specific overdamped case where the amplitude, or rather the oscillation, will come straight from its initial amplitude and find the shortest time possible to just go back to equilibrium with no oscillations. So I'll write that. We could say that there might be some case like this one right here, where this is our critically damped case, where it's the shortest time possible. So this will be time possible to equilibrium with no oscillations. Okay. So the last part that we really talked about in this chapter were driven oscillations and resonance. So the really, really big thing I want you guys to get out of this one, other than the processes that kind of came behind it, were the introduction of natural frequency. So natural frequency, will define by f sub naught. This is going to equal 1 over 2 pi times the square root of g over L for our pendulum case. Or it's going to be equal to 1 over 2 pi times the square root of k over m for our spring. And I'll just note here natural frequency. So what this natural frequency really is it says that based on essentially all the different ways that we could describe our period, and kind of going into just the behavior of the system itself based on its initial conditions, we will find that if there's some amplitude on this side, and let's say this is our frequency on this side, then there's some frequency where if we just kind of put in our initial values, we will find amplitudes that work very, very efficiently for the system. And if you guys decide to take waves and oscillations for the physics courses, there are some really, really cool demonstrations for this. Well, you don't need to actually take the course to be able to see it. If you just look up things like natural frequency demos, there are some really, really cool ones out there. Like if you take a tube and calculate the way that the natural frequency would be, and you just slowly change the frequency on like some audio driver outside without changing the volume knob in the slightest. If you just get to that frequency, the system will start booming, just like it'll sound like somebody turned it up from like 3 to like 13. And you're sitting there like, what happened here? And it's just that everything's moving in pretty much the most efficient way possible. Now, something we can know about this right here is this curve. I'm drawing really 3 here to demonstrate that this is kind of like a packet. And what I mean by that is pretty much there are lines that can be drawn throughout the entirety of this. And the ones that are closer and have a higher amplitude will have a low B value or damping coefficient. And the ones that are really, really low down here will have a high B value. So essentially the ones that are damped more will have a smaller amplitude at their natural frequency. And then the ones that have a very, very high damping coefficient will have a higher frequency, or rather have a higher amplitude at their natural frequency. Okay, so that's really all I had for this. So let's get into the questions. So I think this is good. This question is good for describing exactly how we can decompose our equation that we've been given to find the position of a wave pretty much, or an oscillation. So the question asks, the position of a mass on a spring is given by the following equation. What we want to find is what is the period of the motion? Where is the mass at t equals 0.25 seconds? And we want to show that the mass is at the same location after one period, after one extra period of what we found for part B. So drawing this out, we have some oscillation, right, or rather some spring system right here, mass m, and let's say we're at some displacement, delta x, then we really have all that we need for the system right now. But we're also given that the position is described as 6.5 centimeters times the cosine of 2 pi t divided by 0.88 seconds. So let's kind of figure out what values were just defined in that equation. So we have that our position is going to be equal to our amplitude times the cosine of omega t plus phi. Well, there's no addition going on inside of this. So we can say that our phi value is equal to 0. We have no phase shift. Additionally, our amplitude right here is given to us as 0.065 meters. I just converted the centimeters to meters. But something else we have to know about that is that it's going to be equal to our maximum displacement. And then finally, we have our omega. Now, what we have right now on that side since we know that t is going to not be a part of omega, we'll just kind of not consider our t for a moment. So we get that our omega is going to be equal to 2 pi divided by 0.88 seconds. Well, the equation that we know this by is that omega is equal to 2 pi divided by our period. So we can see by this that our period is just going to equal 0.88 seconds, which just so happens to be the answer for part A. So for part B then, what we want to do is find where the mass is at t equals 0.25. So what we want to do is find delta x at t is equal to 0.25 seconds. And if you think this is trivial, you are correct. This is just going to be a matter of plugging in the values that we already have into that equation that we were just given. So our position is our amplitude times our cosine omega t plus phi. And I'm writing this over and over again just to try and get it in your guys' heads. So we get that our amplitude was given to us as 0.065 meters times the cosine of 2 pi times t, which is 0.25 seconds, divided by our period, which is 0.88 seconds, and we have no phase shift. So plugging this into the calculator, we get that the position at 0.25 seconds, or a quarter of a second, is negative 0.014 meters. Okay. So for part C, what we want to do is show that the mass is at the same location 1 period later. So we want to essentially prove that x1 is equal to x2 if omega 1 is going to equal to 2 pi t divided by t, or a period rather, and omega 2 is going to be equal to the same thing, just a period later. So we get this is going to be 2 pi times our time plus a period divided by our period. So we already know that x1 is going to be equal to negative 0.014 meters. That's what we solved for in part B. But if we consider the second one, well, let's plug it all into the equation that we have. So it'll be a cosine, and then it's 2 pi t plus our period divided by t. Actually, this would be t times omega 1 and t times omega 2. So plugging in the values that we know, we get that this is equal to 0.065 meters times the cosine of 2 pi times 0.25 seconds plus 0.88 seconds divided by 0.88 seconds. And if you do plug this into the calculator, it's exactly the same thing. So we can say that x1 is equal to x2. So main takeaway from this, if we just add a period to whatever time that we are considering, we will get the exact same position. But that is under a very, very crucial circumstance that we don't have any damping adding to the system. Okay, let's go on to the next problem. Okay, so I think this problem does a really good job at describing oscillations and collisions at the exact same time. So let's read what this is asking. A 2.5 gram bullet embeds itself into a 1.5 kilogram block, which is attached to a spring of force constant 785 newtons per meter. If the maximum compression of the spring is 5.88 centimeters, find the initial speed of the bullet. So let's write out really two different situations of what we got right here. Actually, let's make it three. So we have our mass system with some spring, and we are currently at equilibrium. We'll see that this is before our collision. And we have the bullet coming in with some initial velocity, and it's going to collide with it. But now, let's consider the collision. Well, at the moment it collides, we are still at position equilibrium, but we are just going to start to have a force that starts going. So this is when we'll kind of have a turnover from our final velocity that we would get from the collision to what the actual velocity is of our kinetic energy, or our initial kinetic energy velocity. And finally, when we really get into our conservation of energy, then we'll find some displacement delta x with the bullet system already in here and some force of our spring. Okay, so let's start with really defining what else we have given in this system. So our period, it's probably going to be helpful to define it as 2 pi divided by the square root of m over k. We're in a spring system, so we're going to want to define our period like that. Also, we have the mass of our bullet, let's call it lowercase m of b, is 0.00225 kilograms. Our amplitude is going to be equal to 0.0588 meters. The mass of our large block is going to be equal to 1.5 kilograms. Our spring constant is 785 newtons per meter. And that's about all we have. So let's consider this first case. Well, we have our collision. We have a perfectly inelastic collision. They're going to come together as one body. So we can write the collision as the mass of our bullet times the velocity of our bullet, that initial case, plus the mass of our block and the velocity of that block. Well, it's going to equal some combined mass of the two of them times some final combined velocity. So something we know about this is that our velocity of our block is 0 when the bullet has not collided with it yet. So we're going to be able to cancel out this entire term. And knowing that we want to essentially find the velocity of our bullet, that initial velocity, let's solve for this. So we get that the velocity of our bullet is going to be equal to the mass of our bullet plus the mass of our block times our final velocity divided by the mass of our bullet. So this is great. We'll be able to use this at a later time. But thinking ahead a little bit more on top of this, this final velocity is essentially going to be our initial velocity when we're considering our conservation of energy. Because it'll be when our block is starting at our equilibrium state and then moving to its maximum compression. So this will be the velocity that we use. So let's solve it like that. So we get that this V final is going to be equal to the velocity of our bullet times the mass of our bullet divided by the sum of their masses. Okay. So like I was saying beforehand, let's get into our conservation of energy. So we'll stay along the lines of we have our change in our energy is going to be equal to our work done by non-conservative forces. And in this case right here, we're going to say that our non-conservative forces is equal to 0. So we'll get the condition that our initial energy is going to be equal to our final energy. Okay. So our E initial, we have some kinetic energy initial plus some potential initial. And that's going to equal some kinetic energy final plus some final potential. So if we want, when our block is at equilibrium here and at max compression here, all we're going to have is some spring potential for our compression and only some initial kinetic energy. So our gravitation, or our not gravitational potential, our spring potential in our initial state will be 0, and our final kinetic energy will also be 0. So by resolving this, or rather putting it in terms of the pertinent variables, we are going to get that this is 1/2 times our mass of our system times our V initial squared. And that's going to equal 1/2 times our K X max squared. Okay, so what's our mass of our system? What's our V naught? And what's our X max? So writing this in terms of the things we already do have, the mass of our system is going to be the mass of our block plus the mass of our bullet. Our V naught is going to be the V final that we got from the collision. So we'll write this in as our V of B plus the mass of our B divided by the sum of their masses. And then square that entire term. And then that's going to equal 1/2 times our spring constant. And our X max so happens to be our amplitude here. So we're going to square that. 1/2s cancel, makes it a little easier for us. So by simplifying this side right here and kind of putting everything together, we get that this is going to come out to the mass of our bullet plus the mass of our block, our combined mass. But we're going to end up dividing that by our combined mass squared pretty much. So all we're going to be left with is 1 in the denominator. So we get that the initial velocity of our bullet squared plus the mass of our bullet squared divided by the sum of our masses. It's going to equal our spring constant times our amplitude squared. And getting the velocity of our bullet by itself, we get that it's going to be equal to the square root of our combined mass times our spring constant times our amplitude squared divided by the mass of our bullet squared. And by plugging in our values, we get that this is going to be 0.00225 kilograms plus 1.5 kilograms times our spring constant, which is going to be 785 newtons per meter, our amplitude, which is going to be 0.0588 meters squared. And then we're going to divide by the mass of our bullet again, which is 0.00225 kilograms squared. And this gets us a value of 897 meters per second as the initial velocity of our bullet. Okay. I like this equation, or rather this problem. I think it does a pretty decent job at bringing oscillations and collisions together. Okay, and for our last problem. So on the construction site for a new skyscraper, a uniform beam of steel is suspended from one end. If the beam swings back and forth with a period of 2 seconds, what is its length? Okay, so it doesn't really look like it says this, but we're dealing with a physical pendulum. So it says on a construction site for a new skyscraper, a uniform steel beam is suspended at one end, beam swings back and forth, blah, blah, blah. We are considering a uniform beam. We're going to have it with mass M, some length L, and based on what we were saying beforehand, since we're dealing with a physical pendulum, we're going to need that weird L, that lowercase l. So it'll be important here to define our center of mass. It says it's a uniform steel beam. So the center of mass we can assume is going to be directly in the center. So this distance right here will be our L, which will be equal to our total length divided by 2. Additionally, it's probably good to know our moment of inertia. So this is going to be considered a rod, essentially, that's pivoting around its end, not around its center. So that moment of inertia comes out to be 1/3 mr squared. This r is going to be the length of our entire thing. So we get, this is going to be 1/3 times our ml squared. Okay. So we're also given that our period is going to be 2 seconds. And we also define earlier when we were talking about our equations that our period for a physical pendulum is 2 pi times the square root of our lowercase l times g times the square root of our moment of inertia divided by our mass times our lowercase l squared again. Now let's do our substitutions. Period is going to be equal to 2 pi times the square root of lowercase l, which in this case we know now is going to be L over 2, our big L over 2, divided by our gravity, times the square root of our moment of inertia, which is 1/3 times our mass times our length squared, divided by our m, where I am going to write this as an uppercase M now. This is just how it was defined in our equation beforehand. So now let's put it in terms of the mass that we actually care about, which will be this m. And then our lowercase l squared is going to be L over 2 squared. So simplifying a little further, we get that this is going to be 2 pi times the square root of L over 2g times the square root of 4L squared. These masses are going to cancel. 4L squared divided by 3L squared. These L's are going to cancel once again. And we get that our period is going to be equal to 2 pi times the square root of 4L over 6g, which is 2 pi times the square root of 2L over 3g. Okay, this is awesome. Now what we have to do is define this, since we really want to find what is the length of the beam, we want to solve for L. So we get that our L, it's going to equal our period divided by 2 pi. Well, now we'd have a square root on one side. This would be all that we'd have left after dividing by 2 pi. So we're going to have to square the entire thing. And then we'd have to multiply by 3g over 2. And then just plugging in all the values that we have, knowing that the period is going to be 2 seconds. We're going to have to square that. And then we're going to do 3 times our gravity, which is 9.81 meters per second squared, divided by 2. And we get that the length of our physical pendulum would have to be 1.49 meters if our period is 2 seconds. Okay. So this is all I really wanted to cover for oscillations. But I want to tell you guys why I think that this stuff is awesome. And it's because waves make up so much of physics in so many ways. Like you see that we're talking about oscillations here in terms of a physical pendulum. We're talking about it in terms of very, very real things that we've been working with for a very large amount of the semester. So the fact that we can kind of pull this idea of oscillations into so many different aspects of things that we've already done before and will do, it's a nice topic and a nice thought to know that you're going to be dealing with something that's just going to constantly be expanding. People work on this stuff every single day, whether it's optics, whether it's like solid mechanics, whether it's something like even just oscillations, orbital mechanics. Almost anything you could think of in physics has to use this in some regard. And I think that that's really cool. And you're also going to find that this stuff does not go away in 202. In fact, it only builds more and more. And I don't mean that to scare you in any regard. In fact, I mean that as a comforting thing. You're going to go into that 202 or 208 with already a prerequisite knowledge of a lot of these really important topics. So I'm sure this might be the last video a lot of you guys see because it's the last of 4. But I want to say an absolutely enormous thank you to each and every single one of you. You guys have been an awesome class for me. I took on, it was 4 discussion sections and 4 lab sections. So I had a very large amount of you guys for both. It's been a reason for me to get up in the morning to see, or rather hear, each and every single one of your smiling faces. And yes, a smile can come through a phone. But thank you, thank you, thank you. Every single one of you guys are awesome, and I'm grateful for every one of you. Good luck on your exam. Please let me know if you have any questions coming up for the rest of this weekend, and I'll be around for it. Otherwise, it's been a pleasure. I'll talk to you guys later.